Alright, so here we are with lesson number 1 for Unit 2, and we're going to cover probably the first 5 pages of Unit 2 notes. We're going to look at, in essence, the various scientists over the years that are given credit for developing the current atomic theory from the beginning, from the most basic model to the current model, which is called the quantum mechanical model, which we'll get into. You'll see here that there's the vocabulary terms. The ones that are in red are truly the terms that you should know the definitions for. The other terms are not really things that you need to know a definition for, but they are definitely concepts that you should understand as we go through this. So let's look at, and next are the objectives. The objectives are really important because it's almost like a checklist, and when you finish this unit, you should be able to do all of these following things. If there is something here that you cannot do before the test, that's something that you need to ask me about, come for extra help, ask me a question in class, etc. So let's go on and start to look at how the atomic model has evolved over the years. The first definition would be the atom. The atom is the basic building block of matter. Everything that is considered matter, which is pretty much everything, is made up of atoms. Atoms cannot be broken down chemically. The first person who used the term atom, or atomos, back in 450 BC was a guy named Democritus. You're not going to see Democritus' name or his philosophy asked about because he was not really a scientist. He was a philosopher back in those days. The first scientist that's notable scientist is a guy named John Dalton back in the early 1800s. Again, years and dates did not make a difference. He's kind of known as the founder of the atomic theory. And he had 4 postulates about it. You should be very familiar with these postulates, and when I say familiar, you should be able to recite all 4 of these. First, he said that all matter is composed of indivisible particles called atoms. And the term that's important there would be indivisible. The term indivisible in this case means that atoms could not be divided. In other words, atoms were the smallest particles that could exist. Keep in mind, this is Dalton's postulate. It turns out that atoms are divisible. So in this particular case, it turns out that this Dalton's postulate, his first one, is incorrect. Number 2, all atoms of a given element are identical in mass and properties. In other words, he's saying that if you have 1,000 hydrogen atoms, every single one of those hydrogen atoms is going to be identical. Same mass, same properties. And again, number 2 turns out to be wrong because of something called isotopes, which is a term that will become extremely important as we go on. His next 2 postulates are still correct today. Compounds are formed by a combination of 2 or more different atoms. The last one is atoms cannot be created, destroyed, or converted into other kinds of atoms during chemical reactions. So you cannot change one element, hydrogen for example, into another element, lithium, during a chemical reaction. It just cannot happen. It can happen during a nuclear reaction, not a chemical reaction. And chemical reactions basically is 90% of what we look at in this course. So basically, to sum up his theory, which became as the cannonball theory, he said that atoms were spherical. Look at this diagram here. And they had a uniform density. The next person is a guy named J.J. Thomson in the later 1800s. And if you have this ditto, you can just click on this link, but I'm not going to take up the time. The cathode ray tube is not an experiment that they ever ask about on the Regents exam. But it is how he discovered one of these subatomic particles. He discovered the electron. He discovered that the electron is extremely small and that the electron is also negatively charged. His model became known as the plum pudding model. And here's a sort of a diagram of his model on the right-hand side. And the way that they describe it is that you see these blue circles. Those would represent the electrons embedded in the atom. And the orange part would be positively charged matter. So you basically had, it's almost like a chocolate chip cookie. The chocolate chips would represent the electrons. The rest of the cookie would represent the positive charge. He had no idea that there was actually a particle that had a positive charge. He just figured the entire rest of the model of the atom was positively charged. The next person, and this is by far the most important experiment, and it is definitely asked about on every single Regents exam, is Rutherford. Rutherford conducted something called the gold foil experiment, and you can see a diagram of it here. They are not going to give you a diagram and ask you to label it, or explain it, what you're going to have to be able to do is two things. You have to know what his observations were from his experiment, what data did he collect from his experiment, and then what conclusions did he make based on his data. So basically what he did was he shot a beam of alpha particles at a sheet of very thin gold foil. And he expected almost all of alpha particles to pass straight through the gold foil because if you remember in Thomson's model that the mass of the atom was evenly distributed. It had a uniform density, so there wasn't parts of the atom that were very dense that would deflect or block an alpha particle. And indeed, most of them did pass through, but some were deflected a lot, which kind of blew his mind. He did not expect that. So here is his conclusion, and this is really what you need to remember. The first one is that the atom is mostly empty space. The empty space, of course, means that's where the electrons are. Second is that the mass of the atom is concentrated in a very small part called the nucleus, and that this nucleus has a positive charge. He didn't really add to any of the information we had about the electrons. He knew that the electrons are outside the nucleus in that empty space, but that's pretty much it. One of the problems with Rutherford's model is that since electrons are negatively charged and they are outside the nucleus, and the nucleus is positively charged, well, when you have two different things that are oppositely charged, one is positive, one is negative, they're going to be attracted to each other. So scientists said, well, if that is the case, why aren't the electrons, which are negatively charged, simply pulled into the positively charged nucleus and the atom collapses? Rutherford had no answer for that. Well, along came a guy named Niels Bohr in 1913 who said, I know why. Because the electrons are not motionless outside of the nucleus. They are moving around the nucleus similar to the way that the planets move around the sun in orbits. They contain different amounts of energy, and you can actually make electrons move from one energy level to another. We'll talk about that later. If you force an electron to move further away from the nucleus than it normally is in, you have now made it into the excited state. When that electron then falls back down to where it's supposed to be, it's in the ground state. And we'll talk more about this later on when we look at excited versus ground state. Now to the last one. This is the current model of the atom. Again, it's extremely important that you make a note on your left-hand side. The Bohr model is not the present model of the atom. The wave mechanical or cloud model is the current model of the atom. It is a little different than the Bohr model, but not drastically different. Basically, the main difference is two things. The electrons do indeed still, in the wave mechanical model, move around the nucleus, but they do not move around the nucleus in perfect spheres, like they did in the Bohr model. They move around in different shapes. And they, instead of calling them orbits, they call them orbitals. And you do need to know the definition, the real definition for orbital. It's an area of high probability for finding an electron. Because when you have an electron traveling around the nucleus, you can't exactly pinpoint where it's going to be at any moment in time. You have an idea of where it most likely will be, but you can't really pinpoint an exact place. So the wave mechanical or electron cloud model really was developed using the information from many scientists over a long period of time. So it's not one person that is given credit for developing the present day model. And here are some review problems that you can also practice on. It says, which of the following did Rutherford's gold foil experiment prove? Well, let's take a look. That the atom was a uniformly dense sphere certainly did not prove that. That's what Thomson believed. The atom is mostly empty space with a dense positive core. Bingo. Letter B is the answer. 2. J.J. Thomson's cathode ray tube experiment led to the discovery of, well, remember, cathode ray tube led to the discovery of the electron and that it is negatively charged, so that would be choice, looks like D. 3. According to the Bohr model, electrons are found in areas of high probability called orbitals. No, when you're referring to orbitals, that is the current model of the atom. And the answer here would be B. Electrons travel around the nucleus in circular paths called orbits. Number 4, according to the wave mechanical model, obviously A is the answer. Electrons are found in areas of high probability called orbitals. And the last 3, which of the following is not one of Dalton's postulates? let's see. Well, all atoms of a given element are identical. Well, that is one of his postulates. All atoms look like a simple sphere. That is one of his postulates. The mass of an atom is evenly distributed. Atoms of different elements have different properties and masses. Well, let's take a look at, let's go back and look at, that's a good thing about this, you can always go back. Dalton, let's see. Atoms created, all atoms of a given element are identical in mass. Compounds of form, atoms cannot be created nor destroyed, so let's go back and look at it. Get to this eventually. So I'm going to say that it is going to be D. Atoms of different elements have different properties and masses. That is not listed in this thing. That actually happens to be true. Don't really like this question, so we're going to move on because I think there's actually two answers here, but we'll move on. When electrons in an atom gain or absorb enough energy, they can it looks like there's actually more than one answer to this. When electrons in an atom gain or absorb energy, okay, when they gain energy, they're going to move further away. So they're going to jump to an excited state, which is C. When excited electrons lose or emit enough energy, they can jump to the ground state. So when they gain energy, they become excited. When they lose that energy, they go back to the ground state. And excited and ground state, even though we went through them quickly here, you're going to see a lot more of that later on. It's extremely important terms. Okay, so let's stop this one here.